Hello, this is Andy Schweitzer, and this is a small little video running through our chemistry review packet. And I have all the work done. I'm going to post this actual answer key as a uh, resource as well. But this is going to be Speedy Gonzalez through this little review sheet. I've got a bunch of key terms here. I'm going to just run through some of them. Principal quantum number is the energy levels. There's a picture right there. We have ionization energy, amount of energy you need to remove an electron. Hard to see, this thing is a little bit of an odd, thick pen mark, but completely linked to atomic radius. Farther an electron is away from atom, the less energy you need to remove it. Isoelectric, all atoms are trying to gain or lose electrons, become more stable. That generally is of the noble gases, and therefore it is isoelectric with the noble gases. Is generally how we would use that particular term. Same number of electrons as definition. We've made a big distinction between molecules and ionic crystals. Therefore, a crystal lab structure is the picture of a crystal structure. Valence electrons are the outer electrons. Alkali metals is the first family on the periodic table. Hund's rule means as if electrons fill into suborbitals, they fill in separately as opposed to doubling up first. Therefore, we have 3 empty slots here in 2p3. Ground state, I have a picture here of a ground state. Excited state is bumping up into it. Electronegativity is the atoms, attraction for electrons in a bond. Nitrogen, oxygen, fluorine, chlorine are the ones that are big ones. Composition reactions, we put these all together for composition. This is a redox reaction example, metals exchange with metals, non-metal exchange with non-metals, and solubility reactions. That's decomposition is the reverse of a composition, breaks apart. Soluble means dissolve, AQ, odd looking AQ there, AQ. Insoluble does not dissolve, solid oxyacid, type of one of our acids. Diatomic molecules, there are a total of 7 of them that we deal with commonly, and there they are, their natural state. Rotating down to the bottom here, get rid of some of this clutter here for a moment, and alright, there we go. Some of the names. Ionic compounds only give names, so potassium permanganate, hard to see that. Copper, and as the cation, chloride is anion, need a 2 here because there's more than one version of copper, so +2. H2S is hydrosulfuric acid. This is the only that changes. Phosphoric acid, I had to put ic in here because that's phosphate. Sulfur hexafluoride is a covalent compound, 2 nonmetals. We have then the formulas: copper 2 nitrate, charge balanced. Oxygen tetrafluoride, that this tells me that it's covalent, and there it is, right here, oxygen tetrafluoride. We have hydrofluoric acid right here. I have sulfuric acid right here, and I have sodium sulfate right here. Organic introductory, this will be at the very first chapter on. Okay, propane, 3 carbon, C3H8, all single bonds indicated by the ane. Indicate how we know that the burning of propane would be a chemical reaction. Well, there are 4 indicators of a chemical reaction. Heat and gases would be the ones we choose for this reaction. Draw out a structure of a 4-carbon alcohol. I have 2 of them drawn here, and then draw an isomeric version. Would be one in which they're isomers, same alcohol, just alcohol's in a different spot. They have the same formula, C4H8O8. OH. Actually, that's C4H9OH. Alright, moving down here. I did 2 of them here. Iron, symbol, and protons right off the periodic table. Mass number is the total protons and neutrons, all the mass in the nucleus. 57 things, 26 of them are protons, the rest are neutrons. 0 charge, so 26 and 26. Zirconium, look on the periodic tables, 40 and 40, number of protons. 40 plus 93 should be 133. I have 40 protons, 39 electrons, therefore 1 more proton than electrons. And is it for that page. Rolling through here, we have first one here is just electron configurations. Take a look. I gathered 2 more electrons for this guy. Normally be 3p4, 1s2, 2s2, 2p6, 3s2, 3p4. But again, I gained 2 electrons. This is now isoelectric with argon, 3p6. Shorthand, use the previous noble gas. So I have 2 options here. There are some variations of the electron configuration. If you look online, you'll find some slight differences. Those differences are beyond the scope of this class. Orbital diagrams, there's 2 of them here. Using Hund's rule here. The general reason why we do orbital diagrams is to indicate how many times this substance will bond, and it's generally going to be the number of unbonded pair electrons. Trends the periodic table or atomic structure. Okay. Rank ionization energy from smallest to largest. Ionization energy is based purely off of Coulomb's law and the distance of the atoms. Therefore, atoms get smaller as you up the right-hand corner. And I listed the atoms out in order here, and therefore I listed them out. Smallest ionization energy to largest. And this is inversely proportional to the radius. Adding electron to an atom will always make it bigger. True, because electrons either repel to make it bigger, or they add on a new energy level to make it bigger. Adding a proton to an atom will always make it bigger. False, only makes it smaller. Increasing the proton charge, nucleus charge for dragging electrons in, not adding any electrons in that case. Adding a proton and an electron will always make an atom bigger. It's false. It'll make it smaller. It'll only be smaller if no new energy level is created. Adding protons always makes it smaller, even if you add an electron, unless of course you expand into a bigger atomic orbital, then electron orbital, then of course you get a lot bigger. What is Coulomb's law? It's right here. How does Coulomb's law affect metal reactivity? Well, metals want to lose electrons. So if they're bigger, then the electron is farther away, therefore it's easily lost, and therefore more actively it will be lost. These 2 things here will indicate a small ionization energy. There is the answer to those 4. Lewis dot structure. Number of valence electrons. 6, 18, 24. Note the short of electrons, sharing a pair here. No charge, I'll just draw the resonance structures out. Polar bonds, yes. Symmetry, yes. Therefore, the charges in the polar bonds cancel, and we are not polar. What I expect the substance to dissolve in water? No. There's no Coulombic attractions between this this is non-polar compound, so we have no charges, and therefore we're not attracted to the charges of the substances. Next, we have these chemical reactions. It just did this stuff, and there's the answers. There we go. Final answers there, seg figs, and you can take a look.